So in this video we're going to have a look at iron. If you have watched the last video, which hopefully you have, we looked at the manufacture of iron from its ore hematite through the blast furnace. We're going to look at iron beyond its manufacture. We're going to look at how do we actually endeavour to conserve our iron ore reserves, because obviously they are a finite resource. We're using them up pretty quickly. The thirst for iron around the world and steel around the world is huge. So we've got to ensure that for future generations there is still enough iron ore and therefore iron and steel left in order to meet the needs that they will have. And we're going to look at then the pros and cons of the raw materials that are used in the manufacture of iron and the byproducts that are produced during the manufacture of iron. We're then going to look at the chemistry of rusting. Rusting obviously is a huge problem whenever it comes to iron, because obviously it does rust, and iron rusting is a form of corrosion, and that will affect the structural integrity of iron and steel. So we've got to know how the chemistry behind rusting, so that we can actually then design methods and techniques, of which there are already many, to prevent that rusting and conserve the iron that we have for as long as possible, so that we don't have to replace it. Okay, so let's get going. So conserving iron ore reserves. Hematite, obviously, as we've already said, is a finite resource. It's in the Earth's crust, and so we've got to make sure whatever iron we have at the minute, if we are finished with it, it gets recycled. Whatever iron we do have, that it is prevented from rusting so that it can continue on. We don't have to replace it. So those are a couple of ways that we must make sure, and that you can quote to an examiner, how you would look after the iron reserves that we still have left. Okay. The other benefit of recycling iron is, as it says on the screen now, much less energy is needed to recycle a quantity of iron than to produce new iron to replace it from the ore that is dug up out of the ground. There's a huge amount of environmental issues concerned with digging ores out of the ground. If you're recycling ores, you don't have to do that. There's also huge energetics and energy requirements involved, and pollution involved in making iron from hematite through the blast furnace. So if we can avoid all of that by recycling our iron, okay, that can only be a good thing. So the byproducts, let's consider just very quickly a few things that you might want to know about the byproducts before you go into an exam. So slag, we've already spoken about, is that byproduct made by the neutralization of silicon dioxide sand, essentially, okay, which is neutralized by the calcium oxide from the thermal decomposition of the limestone in an acid-base reaction. You should know all of that already, but slag's a byproduct, but it has lots of uses. So it can be used to build roads, and it can be used in the manufacture of concrete, okay, and insulation of cavity walls even. So that's a good thing. Lots of chemists and chemical engineers are always trying to find uses for byproducts of chemical processes and chemical industry. And if you can find a use for a byproduct, that turns it in from a waste into something which is actually useful. It may not have a huge amount of monetary value, but the very fact that you don't have to scrap it, bin it, okay, bring it to landfill, all those sorts of things is a huge burden off your financial bill and off the environmental damage that can be done by chemical processes. The second thing, the problem that we have, are gases coming out of the blast furnace. You get a huge amount of carbon dioxide. You've already looked at the chemical reactions that occur in the blast furnace, and you would have seen that carbon dioxide was a massive gas, or was the main gas that's produced in the blast furnace. Okay, so that's an issue. But what you can do is you can take that hot air and you can use it to heat other things. You can use it to heat the air that goes back into the blast furnace. You can use it for energy source to heat, to produce electricity, or to heat houses, or to heat your factory, all those sorts of things. And clever engineering allows chemical engineers and structural engineers to design processes whereby those things are not actually waste and they're not going into the atmosphere. Because remember, carbon dioxide is a greenhouse gas, and the less of that we can push into the atmosphere, obviously, the better. Coke then, which is the slightly impure form of carbon, which is used as the reducing agent, or to form the reducing agent in the blast furnace. One of the impurities in that is sulfur. Unfortunately, whenever you burn coke in the blast furnace, when it gets very hot, it produces sulfur dioxide. Sulfur dioxide reacts when it gets out into the atmosphere with moisture in the air. cloud water, if you want to think of it that way. And that produces a compound called sulfurous acid, which then gets oxidized further to produce sulfuric acid. Sulfuric acid is a very strong acid, and if it falls back to Earth, it has a huge problem in that it causes acid rain. And acid rain has a whole raft of negative issues on the environment, okay, right from polluting waters where it can damage aquatic life, it can fall on vegetation and damage leaves, which of course then has a negative impact on the growth cycle of plants, so lots of problems with sulfur dioxide getting into the atmosphere. Chemists and chemical engineers have designed a process whereby that sulfur dioxide gas is passed through a scrubbing process. And scrubbing in the chemical industry to gases is exactly the same as kind of scrubbing your floor at home. It essentially cleans it. And the reason why we can scrub this gas, the sulfur dioxide gas, is because, as I've already said, it's an acidic gas, and you can do two things with it. You can scrub it by passing it through a fine mist of water, and that really just still makes acid, but it makes an aqueous solution of it now, which you can bottle up, and you can actually perhaps sell that. Okay. You can also, if you want to, use an alkali, and bubble it through an alkali, and that makes a neutral solution of a salt. Okay, and water, so you can do that, and that makes it essentially environmentally harmless. And that's what scrubbing is. It's scrubbing the same way as you scrub your hands, you scrub your floor, you leave at the end. That's a clean process. Right, let's have a look then at the chemistry of rusting and what rust actually is. So you need to be able to describe rust, of course, first of all. It's very simply, it's a pinky brown solid, nothing more than that. It forms when iron reacts with water and with oxygen. So you need both water and oxygen in order for iron to actually rust. It's a very undesirable process for the simple reason that iron and steel are used very often for structural reasons, to hold things together, to support structures. And if that iron forms rust is a weak, structurally weak, poor structural integrity compound, and it doesn't have anywhere near the strength of iron. It has very little strength. In fact, you'll all have seen flaky rust compared to steel or iron. It's completely different properties. So we need to stop the iron from rusting so that our bridges and our buildings are always able to stand up structurally. Okay, the chemical name for it, what you have to know, is hydrated iron 3 oxide. You will, in the exam, get a mark for hydrated, and you will get a mark for iron oxide, and you will get a mark for having the term 3 in there. 3 just simply means that iron, as you hopefully know, is in its +3 oxidation state. So if our valency, so if we have iron and it's +3 and it's with oxygen, which is of course 2-, iron 3 oxide is of course that. It has a formula of iron 3 oxide, as I've just said, but then you must remember the dot formula to show that it's hydrated, that it has XH2O. X just stands for a variable, by the way, for those of you who don't know. So what do we need for iron to rust? Well, we need water and we need oxygen, both. It won't work if it won't rust if we just have one of those. Must have both of those, and you need to be able to describe a practical to test to prove that both of those are in fact required for rusting. This is the sort of general practical you'll see in textbooks, you maybe carried out in class, okay, that you really have to know. So in the first test tube we've got iron and we've got air and we've got water. Air obviously contains oxygen, and you can see the nail has of course rusted. In the second one we have boiled the water. And when you boil the water, what that does is it removes any, okay, so if we look down here, it removes any dissolved oxygen. Now you will get a mark for saying removing oxygen, you will get a mark for saying remove dissolved oxygen. So don't just say it removes air, that will get you no marks. It must be removed dissolved oxygen, okay? And you'll see there's a little layer of oil put back on the top, and the reason for that is because if you didn't have that, oxygen would simply diffuse its way back into the water, and that would mean that you had oxygen, you had water in your experiment, so it would be an unfair test. And you can see there's no rusting there for the simple reason that there's no oxygen in the water, so there's no oxygen getting to the iron nail, so there is no rusting. The last one, we have air in the atmosphere around it, so we do indeed have oxygen here, but we have a thing called calcium chloride. We probably should have written here In fact, I would encourage you to do so in your exam. Anhydrous calcium chloride. Anhydrous means without water. And what anhydrous calcium chloride essentially does, it acts as a kind of a molecular sponge where it sucks up water, it actually absorbs it. So any moisture that's in the air there, that will take the moisture out of the air and lock it into the calcium chloride. That will form a compound called hydrated, which means with water, hydrated calcium chloride. You'll see a little sachets whenever you buy new shoes or a handbag or something like that that's been in a ship or a container for a long time. And if those little containers, little packets that you find in there contain anhydrous, maybe calcium chloride or something similar to absorb moisture. The reason for that is if those shipping containers come with your handbag or your shoes or whatever from as far away as China or America or wherever, moisture will get into that shipping container and into the box with your shoes, your handbag, or whatever it might happen to be, and will cause it to start to smell and get fusty and pretty unpleasant. So they put little packets, you'll have seen them, of calcium chloride or something, so usually silica gel actually, and that just absorbs the moisture and keeps them nice and fresh. So how do we prevent rusting? Well, essentially you got to prevent it by stopping either water or oxygen getting to the iron. Generally we stop both things getting to the iron. It's kind of difficult to stop one without the other, but there are processes in which you just stop one. We'll have a look at those. So number one, oiling, which is called a barrier method. Okay, so you cover it in oil or grease. You simply cover it to oil or grease, and that stops oil and grease are waterproof, and that stops any water or any oxygen getting to your iron, whatever it happens to be. If you are asked for a method to prevent rusting of iron, guys, make sure that you actually talk about something that is sensible. So, for example, if the examiner said, how would you prevent a bike chain from rusting? Some people in the past might write, painting it. Well, painting it's quite a ridiculous answer, because once that bike chain goes around the cogs a few times, the paint will start to crack off. So you've got to have something that is a sensible answer. So oiling and greasing would be reasonable for a bike chain. Painting, well, that's lots of things, steel railings around your garden or something like that. Yeah. Again, you wouldn't, and again, oiling or greasing would be a ridiculous answer for those, because no one wants oil or grease on their garden fence or their garden gates or whatever. Okay, so always pick a sensible answer. You have galvanizing, okay, which is again another barrier method. Okay, all right. So galvanizing is basically you take your piece of metal and you cover it with zinc. Okay, and what actually happens is the zinc reacts with oxygen in the air to form zinc oxide, and the zinc oxide is a very unreactive inert compound, and it basically coats the iron below it with that layer. And if any of that gets chipped off, that's fine, because what happens is any zinc underneath that layer will continue, because it's more reactive than iron, it will continue to react with the oxygen in preference to the iron. So the iron stays underneath the layer of zinc unaffected and doesn't corrode. It's not very pretty looking, so you wouldn't use it. For example, I think you couldn't coat it for your garden gates or your fence like we have there. It would be a little bit unpleasant looking. You can see it there on the screen. Okay, painting for those things is again much preferable. Okay. We then also have a thing called electroplating, and electroplating basically means that you take a layer of nice, pretty metal. Okay, we've got chrome here, so you'll probably all have chrome taps at home. So you've got a horrible-looking iron tap underneath that, and iron is not a pleasant-looking metal, but we can coat it in a very thin layer of, in this case, chrome metal, chrome-plated, and that makes it look very, very pretty. Okay, easily cleaned, doesn't rust. And it's not overly expensive to have that nice and shiny. Okay, so you've got your plating, electroplating. That can be done. You'll have jewellery which is silver plated or gold plated. Follows the same sort of process. You have vinyl covering. Okay, so basically covering something with plastic. Your bicycle handlebars in part might be covered in some plastic. Okay, you can see a fence that we've put on the screen there, covered in plastic. Again, a barrier method stops any of the oxygen or the water getting to it. And finally, we have alloying. You'll see lots of iron alloyed. That basically means that it's mixed with another element. It doesn't have to be another metal, but it prevents it from rusting, gives it other properties as well. perhaps, but you will have like things like stainless steel that you might have your pots made out of at home, where it's mixed with chrome. Okay, so not coated. It's not a barrier method this time alloying. It's just mixed with it, and that changes the properties of it a little bit. Okay. Right, another method that is not a barrier method is a sacrificial method, okay, which can be used in certain conditions. And basically you plonk a big lump of a more reactive metal onto the iron, and the water and the oxygen in the atmosphere around it will react preferentially with that sacrificial metal. Okay, you can also use powder coating. You get, if you've got maybe like sort of very nice gates on the entrance to your house, they will tend to be powder coated. They look like they're painted, but they're actually not painted. They're covered in a dry layer of little polyester beads. Gives a really strong and durable surface, which again prevents any oxygen or water getting to the iron. And it looks really well. It's actually probably nicer looking than painted. You can see here we've got a ship with sacrificial protection. These are big blocks, probably of zinc or magnesium, can't quite tell, but something that is more reactive than iron, and those things will react sacrificially under the water. This ship's probably just been done and it's about to go to sea. They'll take that out of the water. Divers will go down when that ship is in port, or even out in the ocean. They'll go down, they'll check, they'll keep an eye on those blocks. If they start getting too small, the ship will be brought back into harbour. The old pieces of metal will be removed, and they'll put new pieces of magnesium or zinc. So you'll see that ship is both painted and it has those sacrificial blocks of magnesium or zinc on it, because if your ship starts to rust and it's a multi-million-pound ship, it's really going to be a big hassle. So they take extra steps to ensure things like that don't rust. They're a little bit more important than your garden gate. There's some more, just another photograph of some sacrificial protection. Okay guys, those are all the things that you need to know about rust, its chemistry, how to prevent it, how to conserve our stores of iron within the Earth's crust, our hematite. Okay, so make sure you know that, okay, and I hope I explained that all well for you. Okay, all the best.